Hi, you guys. So I'm going to spend some time going ahead and going over some of the reversible reaction stuff and some of the Le Chatelier's principle, just because I want you guys to have a good idea of what some of these things mean and how you guys can go ahead and how we can use them. First and foremost, reversible reactions. Most of the stuff we happen so that means that the reaction pretty much goes one way, and that reaction goes ahead and it combines to form some sort of product, right? So basically, if we were to kind of go ahead and if we were to kind of look at this, one way that we can look at this is like a regular reaction. We can imagine we have like A plus B makes C, right? And it's pretty much A and B can be anything and C can be anything, right? So that is kind of the reactions that we've been working with, right? But there's another type of reaction in which the arrows can go back and forth. So you kind of see this funky arrow. And basically, that means that yes, A plus B can equal to C, right? And it can go this way, or it can go this way, right? And that's what this arrow means, is that the reaction can go either way. And what happens is that it just means that once you get to C, this product that you make can also break down and it can go backwards into the reactants. So that's why we call it a reversible reactant. So you have to think about it as if the reaction can be reversible, right? So can you basically like kind of go back on it? So some of the examples that you guys looked at back is like cake baking, right? So if you make a cake, right, can you go ahead and can you like somehow magically make it go backwards and the cake will not be baked anymore and then you can get back down to eggs, flour, and all of that, right? And the answer is no in that case, right? That we can't go ahead and we can't do that. Same thing with scrambled eggs, right? Scrambled eggs, you can't really do that. Right. Water evaporating when being heated into a closed container? Yes, right. This one would be an example of a yes one, right? Because if you evaporate water, right, and if the container is closed, some of the water like at the lid, so if you ever like lift like the top of the lid, right, you guys will see that on the lid, right, you get all of these little water molecules, which is the liquid water that you started out with, right? So that would be something that is like an example of something that's reversible, right? And then this section, you guys are going to go ahead and explain pretty much why it's not reversible, right? And then same deal on here. We talk about a beaker that's half full of water. The beaker is sealed with cling wrap. Some of the water is evaporated into gaseous H2O. At some point, the rate of gas forming will equal the rate of condensation, right? So same thing like I was talking about earlier. So you guys know that when you guys are cooking something, right, and if you put a lid on it, once you guys put a lid on it, you guys will see that over time we'll get like at first you'll just kind of cloud up, and then little by little you'll start getting like drops of water that can like kind of like drop in, and that is like the condensation that happens. So that is pretty much the big thing on there, is that you will see that if it cools, all your water vapor will go ahead and will condense back into liquid. So same thing that happens in the clouds and all of that, right? If you heat it up, right, it will evaporate. But if you cap it, right, you're going to capture everything that you are condensing. So that's going to be pretty much the same thing. And again, you guys have to remember that stuff can't be created or destroyed, which means that you're going to start and end with the same amount of water if you are going ahead and if you are putting a lid on it. If you don't put a lid on it, then you lose it to like the universe, but it's still in the universe somewhere. Okay. So yeah. So if you look at this, one thing that I want to point out is that what these L's and G's have stand for, and then some of you guys have noticed this before in some of your equations. So there's basically a couple things. The L means liquid, the G means gas. The S, you guys will see, sometimes it's going to mean solid, and you are also going to see AQ, which is aqueous. I totally butchered that. So aqueous means that it's like a mixed in. So if you, example of something that's aqueous is like salt water. So the water and the salt are like already like mixed together. So that's like an aqueous solution. And there's many things in chemistry that are salts that you can go ahead and you can combine. So in this case, they're asking you if we're talking about liquid water to gaseous water, right? In which direction does adding heat drive the system? So basically, you're going to say, is it left or is it right? So if you heat liquid water, right, is it going to go to a gas? Is it going to go to a liquid, right? And then same thing on there. Does it go to left? Does it go to right? All right. The next thing on here is the dynamic equilibrium, right? So this is kind of what we refer to as a top with a reversible reaction. So some reversible reactions, the key word with dynamic is that they are equal to each other, right? So the forwards reaction, so the rate that I'm going this way is equal to the rate that I'm going this way, right? So that is like a dynamic reaction. So what you'll see is that in these dynamic reactions, it'll look like there's no change that is going on, but in all actuality, it is a change. So there's a couple of examples that you guys have seen already before. For example, in the water cycle that we talked about last unit, same thing, the evaporating water, so the amount of water that's evaporated from the ocean, it goes up into the clouds and then it precipitates down, right? So we have our Mr. Sun here, right? The sun goes ahead and it evaporates water, right? That evaporated water, right, goes to the clouds, right? And then the clouds go ahead and it rains down, right? And you have to keep in mind that it's the same amount of liquid that's going back and forth, whether it falls on like one part of the world or the other, right? But we're not like essentially losing or making anything. What is happening is that it's happening all the time, right? So it's raining somewhere in the world at some sort of rate, at the same rate that all the water is evaporating off of the ocean. So you don't really notice the evaporation so much. You might not notice how much it rains all over the world, right? But it's still happening all over the world at the same rate. So it looks like things are pretty much status quo, but in reality, they're kind of like moving back and forth. Another common reaction is something that you guys see in soda. In soda, how they make soda taste good, in some people's opinion, is that they go ahead and you have all of these little CO2 bubbles, right? And then you have some space in the soda can. If you guys have noticed or bought like a 2-liter bottle, you guys will see that there is also all of those little bubbles inside of the liquid, right? What is happening is that there is carbon dioxide that's dissolving into the liquid and carbon dioxide dissolving out of the liquid. And it's happening at the same time. So when that thing is happening at the same time, what you guys will see is that it doesn't look like there's anything going on in the soda in all actuality, but what you guys will see is that some of it is released into the environment and some of it is dissolving back into the actual soda. But when you actually open the soda, you actually change some of the equilibrium that you have, right? So another example that you guys will see down here is an actual equation. and you guys are going to have to go ahead and you guys are going to see like, okay, I'm creating the NO2 and the CO2 and I'm breaking it down, right? So a dynamic equilibrium is basically switching it back and forth, and you're making it and destroying it at the same rate. So it doesn't look like there's anything going on, but there's actually still a chemical reaction. The next thing that happens is the Le Chatelier's principle. Basically, this is a French chemist's idea. And basically, it says that when a system is at equilibrium, it is subject to change temperature, pressure, concentration, or volume. So basically, what happens is that if you change the temperature of a reaction, if you change the pressure of a reaction, concentration, or volume, you can basically influence, right, what direction the actual reaction is going to go. Is it going to go this way, or is it going to go this way? And that's basically like what is happening with La Chatelier is that we are going ahead and we're going to talk more about how we can go ahead and how like we can make a reaction go one certain way. We can do this with, again, temperature, pressure, concentration, and volume. And I'm going to spend a couple of minutes kind of going through how we can go ahead and how we can do that, right? And basically, we call these like stresses to a reaction, and how we can use these stresses to go ahead and to kind of promote a reaction to happen. Okay? So what we are looking at in this first picture is this. We have H2 and N2 makes an H3, right? So that is what's happening in this reaction, right? In this first reaction, right, we have our H's that are floating in here and our N2s that are floating in here, right? And what happens is that we go ahead and we apply more pressure, right? So this is what this thing means, is that we're applying, this is more pressure. And when we apply more pressure, what you guys will see is that we are pretty much forcing this reaction to happen because we're having more of these molecules collide, right? So if there's more pressure, there's going to be more collisions. And since there are more collisions, right, we're going to go ahead and we're going to promote the reaction. So basically, we drive, right, this equation forward, right? If we lessen the pressure, right, so if we go less pressure, right, the molecules are more spread out, right? And now there are less collisions. And if there's less collisions, right, that means that is ultimately less reactions, right? More pressure, more collisions is more reactions, right? And that drives the equation this way, right? If you put more pressure, there are more collisions and therefore more reactions. So that's how pressure can influence it. And depending what you want in a lab, right? So if you go to like a super fancy chemistry lab, you can actually promote equations that way, promote like a certain reaction. So if you want a certain reaction to go a certain way, right? One of the things that you can do is to kind of put it into like a little pressure chamber, change the pressure, apply more pressure, and you will get the reaction that you want. So it's the same thing on here, right? We're talking about this hydrogen iodine. It's almost pretty much the exact same reaction, right? Which direction, if you had more pressure, how would that go, right? If you had less pressure, how would that go? So those are some of the different things that you guys see on there, and this is just another example, except with some of the different ions. And again, the AQ, don't let it throw you off. It's aqueous, right? So that means that the H plus and the OH are floating in solution. So you can imagine like the little H pluses and OHs, right? They're all floating in a solution. So if you guys need to kind of see that, that is kind of what it looks like, right? So that's what aqueous means. Aqueous is just that it's floating in solution, right? So another way that you can influence a reaction is with a concentration. I've kind of asked you guys what concentration meant in the beginning of the year, and not many people were able to describe it. So I kind of want to go over what concentration is, and then after we'll talk about how that influences the reaction. So concentration is basically how much of a certain molecule you have. So this is just a good example of looking at concentrations. And again, when we talk about concentrations, it's pretty much relative to one another, right? So in this case, I'm comparing the solute, which could be some sort of salt or whatever, and you have to remember that solute is something that dissolves in water. And I'm comparing the solute molecules to the water molecules. And if I have a high concentration, right, so in this case, on this side, I have a high concentration of water. That means that I have a bunch of these little guys that are in here, right? And all of these water molecules that I have on here, that means that I have a very high amount on this side, and it is compared to, right, this side. So if I compare and contrast on this side, I see that I have a low concentration, right? And again, right, when we're talking about concentration, you have to be able to compare them to one another, or else it doesn't like quite work out, because you have a high concentration, right, compared to what would be always the question that can be asked of you, right? Same thing with solute, right? If you look at the solute, I have 1, 2, 3, 4 on this side, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 on that side, right? So on this side, I have a high solute concentration, and I have a low solute concentration. And concentration is sometimes noted like that, 2 brackets. Again, it's comparing it to one another, right? I'm comparing it to the water. I can compare it to the other solute, right? But you have to remember that solute concentration ultimately is relative to one another, right? So how this relates to some of these chemical equations, right? If you guys are relating this to some of these chemical equations, what you guys will see is that we can change the concentration or the amount of a certain molecule that I have, right? And if I have more on one side, right, the equation's going to go and go and go until I run out, until I hit my limiting reagent or whatever, right? So if you look at this, right, if I put in more of this, I'm going to ultimately get more to NO, right? Same thing on here, right? If I change it, right, and if I put more NO, right, into like my reaction, right, then I can drive the equation this way so that it goes and it breaks down to N2 and O2, right? So I can basically change how much I have on each side so that the reaction keeps on going, right? So this is kind of like a more complicated reaction. So this is hydrochloric acid, right? And if I add more HCl, right, to oxygen, I'm going to get more H2O and more Cl2 until I run out of stuff, until I hit like my limiting reagent, right? Um, Same thing on here, right? If I add more oxygen to the equation, I'm going to get more H2O and Cl2, right? So those are kind of like the things that are going to happen, right? If I want to drive the equation the other way, right, I'm going to probably add more water to my equation, right, so that I get more oxygen and more hydrochloric acid, right? So the thing is that basically in this case, right, you are just adding in whichever molecule in order to kind of derive your reaction one way or another. And that's kind of one of the things that Le Chatelier found, is that you can drive an equation one way or another, depending on how much of a molecule you have, right? I'm going to go through this last problem with you. I'm going to kind of set it up. I won't finish it for you. I'm just going to kind of give you guys a quick refresher, because you guys do need to know how to do this. So yeah, you might see a question like this on the final. So it says a scientist wants to produce 20 grams of HCl. How many grams of water need to be added to the reaction? Right? So I want 20 grams of HCl, right? I need to go ahead and I need to find out how many grams per mole, right, of HCl. Then I'm going to use my mole ratio, right, and figure out how my moles of HCl is related to my moles of H2O, right? And then I go ahead and I bring it back down to grams of H2O is mole of H2O, right? And then that would be like, it's that kind of problem that you guys would have to set up. So just make sure that you guys show your work. One last thing that I didn't cover on Le Chatelier's principle, ultimately is temperature, but your temperature stuff should be review. I think I might have skipped it actually. Yeah. So one of the things that you guys will see is that I didn't do temperature. So I'm gonna kind of use it's pretty much almost the same thing as pressure. So an example is you guys going ahead and heating a reaction. So when you heat a reaction, it's basically this same concept, right? So a reaction, say we have a reaction that is happening in our beaker, right? So I'm going to draw two beakers and a couple of things. So I'm going to write temperature on here. So I have two things. It can be okay. So I have these guys that are floating, right? So I have some of these molecules that are in here and they are floating around. So these molecules are floating around, right? I mix these two molecules. So I can go back into my N 2 and my H2, and I should color code them, and my H2, and say they're floating in this beaker, right? And I got them going on there, right? I got a closed lid and all of that, right? If I have them at like room temperature, right? So say if this is room temp, right? These molecules are moving, right? And all of these molecules are moving, right? And some of them might bounce off against the walls and some of them might collide into each other, right? But only the ones that go ahead and that collide are going to be the ones that actually form a reaction. So you have to remember, like I said on here, if you have more collisions, you have more reactions, right? So ultimately, this one is going to have less collisions and it's going to have less of a reaction. And that's kind of like one of those things that we talked about earlier in the year, in which we talked about if you go ahead and if you heat something up, you're going to make the reaction go faster, right? It's the same thing on here, right? If I boil it, right, or if I heat it up, say if I go ahead and if I go to boiling, which is 100 degrees Celsius, right, all of these molecules are moving so much faster, right? And since they are moving faster, they are more likely to go ahead and to bump into each other. And again, like I said earlier, right, the more collisions that we have, right, the more these molecules are going to react. So then we're going to have more of a reaction. So what you guys will see in a lab or even in like some real life situations, right? If you want to get like something to go faster, you go ahead and you heat it up, right? And it's the same thing, right? So you might heat up a reaction in order to kind of influence the reaction to go either one way or another, depending on what you need at that time. So that is pretty much like the basics of the Le Chatelier principle, is that you can use temperature, pressure, concentration, or volume. Volume and pressure go together, right? So if you have more space, then there's going to be less collisions, basically. And if you have less space, you obviously are going to have more of a chance of collision. So again, you got to think about it as chance of collisions. How many molecules do I have, right? The more molecules I have, the more likely they are able to collide, right? And the more likely my reaction is able to go one way or another. So it's basically, it comes down to like space and being able to get these molecules to collide to each other. Okay. So, last but not least, I got the common ion effect. So on some of these common ion effects, what we're talking about is basically dissolving salts, and basically going ahead and talking about how far a reaction is able to go ahead and to go when they're like dissolved. I first want to go over this picture down here, right? So an unsaturated solution, right? I have this liquid and I'm dumping in the salt, right? And I dump in this salt until it goes ahead and until like the salt like dissolves, or it could be sugar. Any crystal really is dissolving, right? My solution is considered saturated once you see that none of it is able to dissolve anymore. So once none of it's able to dissolve anymore, right? Then what you guys will see is that it's considered a saturated solution. So you guys have seen it before when you guys are like mixing something and there's still like stuff at the bottom and it's still there, that solution is saturated, right? So one of the ways that you get it to like go is, again, you mix it or you can heat it up, and that's the same thing as getting the molecules agitated, more likely to collide to each other. But eventually it does get to a point in which it is super saturated. So that means that pretty much you can add and add all you want, but in the end you will get these crystals, right? So I have to go over that so that you guys understand what soluble and stuff means when we're talking about that. And then what you guys will see in some of these equations. Okay, got it. Okay, so we have some sort of beaker here, right? And I am dissolving an NaF, so sodium fluoride, and I am dissolving a calcium fluoride, right? And when I go ahead and when I dump this into a beaker and I'm trying to dissolve this salt, and as you guys know, salts go ahead and they dissociate, or they're kind of like taken apart in a liquid, right? Because water is slightly charged, it goes ahead and it dissolves. So my first salt is going to go ahead and dissolve into sodium fluoride, so it dissolves into Na plus and F minus. My second salt dissolves into K plus and F minus as well, right? So what you guys will see is that I am going to accumulate a lot of these little F minuses, right? So if I keep dumping the salt, I'm gonna end up with all of these extra F minuses. I'll have the NAs and the Ks to kind of counter it, right? But I'm gonna end up with pretty much double, right, the F minuses. And what will happen is that eventually, over time, right, none of these solutions are going to be able to dissolve anymore, right? Because I have way too much F minuses, right? So because I have so much of these guys, it will pretty much like kind of like slow down how much we'll be able to like dissolve into that solution, right? So that is pretty much what happens in the common ion effect, right, is that you pretty much end up with double that. And then what will happen is that your solution pretty much saturates more rapidly because of that. And there's like a couple minute video that you guys can go ahead and you guys can look at, and you can see how that affects it. So it's the same thing on this last picture, right? I'm looking at this last picture on here. I dissolve salt, and then I add this, which is like that silver chloride. And eventually what you guys will see is that you will saturate the solution because you have so many C minuses, right? And if you go ahead and if you do it that way, again, because of the concentration and because you're changing the concentration, you also change which direction, right, this thing is going, right? Because if you have so much F minus, eventually you're going to drive the reaction this way, right? Because you have so much of that in your solution. So that's kind of like the big thing, is that if you're dissolving stuff with a common ion, what you will see is that you pretty much drive the reaction either one way or another. So that is pretty much some of the things that I wanted you guys to kind of review. If you have any questions, please feel free to reach out, and I hope this video helps you guys out a little bit.